Hello, my name is Hyeongseok, and thank you for attending my presentation about the ScaleNet. The ScaleNet is a scalable neural network or scalable deep learning approach in predicting future trajectory of the multiple surrounding vehicles for autonomous driving system. Also, it considers the randomly varying number of surrounding vehicles. This work is the joint work between the KAIST and Hanyang University. This is today's outline. Firstly, I will emphasize about the necessity of the scalability in autonomous driving system. Then I will point out the problems in the previous works about the scalability. After that, I will, before showing the details of the ScaleNet, I will summarize the previous works. Finally, I will show the performance prediction of the ScaleNet with the simulation results at the end of this presentation. Let's see these three figures. As shown in these figures, you will face this various traffic density during driving your car, and you will overcome this situation by using your own deep learning model, which is very most intelligent and fantastic model, which is your brain. Therefore, the autonomous driving system also has to be conscious of the variability of the number of surrounding vehicles as well. In other words, the trajectory prediction model should be able to accept the historical states of the randomly varying multiple surrounding vehicles for generating future trajectories of each car. In other words, the model has to be capable of the unspecified number of the vehicle which is varying in a real time. However, there was no previous works which handles the analysis on the scalability of the models. Therefore, at the first of this research, we evaluated the previous approaches based on the scalability by observing the prediction performance under the varying number of vehicles in a single driving scene. Since the non-scalable model uses the exact physical states of the target vehicle, such as position and velocity, etc., they show higher ability to interpret the kinematics or individual maneuver of the vehicle rather than interaction effect among the whole traffic scene. On the other hand, fully scalable approaches which use the integrated scene representation method shows a higher performance in capturing the traffic level interaction context. However, they are not good at capturing the individual maneuver of the single target vehicle. As a result, you can see in the graph in the below, we found that there is a trade-off effect between scalability, computation load, and prediction performance. To summarize this trade-off effect, I will show this table. For the non-scalable model, the prediction performance is very good in low traffic density situation. Because since they are concentrating on prediction single vehicle, the computationally very light. However, when the traffic goes very complex, the prediction performance will be decreased, and they will require the multiple iteration because there is a lot of vehicle in a single driving scene. However, in case of the fully scalable model, they shows very good performance in a high density traffic. However, they are very inefficient model because they are very computationally heavy. To overcome these two models, there is another approach which is called the partially scalable model, and they shows very good performance over in the various traffic density. And computationally, and they require the iteration is not so bad. However, the key point is the trade-off still remains among these three models. Excuse me. And however, in the proposed approach, the ScaleNet, the trade-off is broken. As shown in this graph, the ScaleNet shows very low prediction error and low computational time. Nevertheless, the vehicles in a single driving scene changes. Also, the performance of the ScaleNet is very consistent and it's very robust. In other words, the scalable is fully a scalable architecture with respect to the number of vehicles. Also, the ScaleNet can mitigate the trade-off effects among the various performance measures. As a result, this model is able to robustly and consistently applicable to any level of traffic complexities. Before I introduce the details of ScaleNet, I will categorize the previous works. Firstly, the non-scalable trajectory prediction model. In non-scalable models, states of the vehicles is represented by using the vectorized form based on exact physical signals. Therefore, they are very good at capturing the kinematics of an individual vehicles, whereas the interactive feature from the whole traffic scene is hard to be captured. Also, they are computationally light. However, they require the multiple iterations for the multi-vehicle scenario. In order to secure the scalability, the integrated scene representation frameworks are introduced. In this paper, traffic situation is expressed in the occupancy grid map. The second paper uses the semantic image with multi-channel for representing the vehicle states as well as the road geometry. Therefore, these approaches is able to capture interaction context from the traffic level. However, since the rasterized representation contains lots of unnecessary area for trajectory prediction, so this model is very heavy and inefficient. Recently, to develop more flexible model compared to the previously introduced works, partially scalable approaches are introduced. These papers use the hybrid approach in representing vehicle states. They encode individual maneuver or individual kinematics using the vectorized form of the vehicle states. After that, the rasterized format is constructed based on the context which is extracted by using the vectorized form. These models are scalable up to predefined number of the agents, which is usually 6 or 7 vehicles. However, the trade-off among the performance measures still remains. This table shows a summary of the previous works. As shown in the below, compared to the previous works, the proposed scale is able to show higher performance, securing the consistency and the scalability. From now, I will introduce the details of the scale. This figure shows the overall architecture of the model. In graphical modeling, traffic graph is generated from the observation, and the traffic graph is embedded into the context by using the EGCN operation. Finally, LSTM-based encoder-decoder architecture is applied to generate future trajectory. Then let's start from the graphical modeling step by step. In the graphical modeling, traffic graph consists of node feature matrix, and each feature matrix is generated by using the observations. In our approach, node feature matrix consists of the position and velocity and heading angle of the vehicle. In each feature matrix, the relative states between every two vehicles connected by the edge is included. So this edge feature matrix edge feature matrix means the interactive feature or interactive context between the every two vehicles, which will be embedded into the context vector by using the EGCN operation. And in EGCN operation, there is a fully connected attention mechanism in order to generate weighted adjacency matrix. By using this weighted adjacency matrix and node feature matrix, the graph convolutional neural network for generating context vector of each vehicles. This context vector implies the interaction effect from the whole traffic scene onto this specific single vehicle. In this stage, there is two trainable weights which will be trained in the training stage. After that, the conventional LSTM encoder-decoder architecture is applied in order to generate time serial future position of the surrounding vehicles. Then I will show the performance of the ScaleNet and the simulation results. This is a simulation, this is a prediction accuracy analysis. As shown in this table and the graph, the proposed ScaleNet shows the lowest RMSE error and shows the the best performance in the enhancing ratio compared to the baseline model, which is vanilla LSTM. And then we also concentrate on the scalability analysis, as shown in these two graphs, which implies the information time and prediction error. The ScaleNet shows the best performance in consistency and robustness. Also, they can securing the high performance. Finally, I will show the simulation results. The ScaleNet is compared to the vanilla LSTM-based sequence-to-sequence prediction model as shown in these figures. We use the NGSIM dataset, and I will show two case studies. First case is a suddenly stopping scenario in lane keeping scenario. During the lane keeping scenario, the sudden stop occurs around the ego vehicle, which is colored yellow. And in this scenario, I want to see how model will react on the situation with the very highly longitudinally interactive situation. For second case, there is a lane keeping scenario with the cutting out edge vehicle. The vehicle behind the ego vehicle will accelerate after the cutting out. You can see that accelerating maneuver in here. So with this case, I want to see how the model will predict the acceleration maneuver as soon as possible. Throughout the simulation results, there is a lot of graphics as shown in here. And the most important thing you need to focus on is these two graphics. The orange dot represents the future position of the surrounding vehicle, which is generated by the vanilla LSTM, and red dot is the future trajectory of the vehicle generated by the ScaleNet. Then let's move on. Let's start from the case one. At this stage, there is the vanilla LSTM is very not robust and very fluctuating for prediction results as shown in this red area. However, the ScaleNet is very consistent, very robust prediction results. And let's move on to the case study 2. And as I mentioned earlier, the vehicle behind the ego vehicle will accelerate after the cutting out maneuver of the ego vehicle. In this figure, please concentrate on the orange dot and red dot. The vanilla LSTM cannot predict the accelerating maneuver of the vehicle behind the ego vehicle. However, the ScaleNet captures the accelerating maneuver very quickly. In conclusion, the ScaleNet is fully scalable with respect to the number of vehicles, which can be robustly applicable to any level of traffic density. And most importantly, the trade-off effects among the various performance measures is mitigated. And finally, inter-vehicular interaction is also considered by using the EGCN-based embedding network. However, the model is not scalable with respect to the road geometry, and also the future trajectory should be multimodal. These two issues will be solved in the future work. This is the end of my presentation, and these are references for this presentation. And thank you for your attention. If you have any question, please contact by my email. And then finally, I want to say thank you to Jeon, Choi, and Dongsuk who advised these works.